In the far future, cosmic expansion halts. Galaxies no longer race apart, they fall inward. Gravity overtakes dark energy, stars collide, black holes merge. The universe becomes a collapsing furnace, compressing all space and matter into a blazing point. Time itself seems to fold inward, but instead of vanishing into a singularity, the universe does something unexpected. It bounces, a new Big Bang erupts, space-time unfolds again, birthing a universe anew. This is the Big Bounce, a radical idea that reimagines our origin not as a beginning from nothing, but as a continuation, a cycle, a heartbeat of the cosmos. One universe dies, another is born. The Big Bounce suggests that our universe is not the first. Instead, it may be one of many in an eternal series. Each universe expands, slows, collapses, and then bounces, giving rise to a new expansion. In this model, the Big Bang was not a true beginning, but a transition point, the result of a previous universe collapsing under its own gravity. The bounce avoids the infinite densities and mathematical breakdowns of a singularity. Instead of an absolute beginning, time stretches beyond the Big Bang. This theory directly challenges the traditional view of the Big Bang, which suggests everything emerged from a singular point of infinite density and zero volume, a point where physics, as we know it, no longer applies. More than just a tweak of the standard model, the Big Bounce paints a picture of the universe that is eternal, renewing itself endlessly. If correct, it would mean that time is not a straight line with a beginning, but a loop or wave that pulses forever. Einstein's general relativity predicts that a universe collapsing under gravity should end in a singularity. But this is where classical physics breaks down. To understand what happens at such extremes, we need a theory of quantum gravity, one that unites quantum mechanics with relativity. Loop Quantum Cosmology (LQC) treats space-time as not smooth and continuous, but made of tiny discrete loops, quantized units of space itself. As the universe contracts and approaches Planck-scale densities, these quantum effects grow stronger. Gravity, which once pulled everything inward, begins to act differently. At the threshold, a new force arises, quantum repulsion. Instead of allowing the universe to collapse into a point, this repulsion halts the contraction and causes the bounce. The result is a transition into expansion, what we perceive as a Big Bang, but really a rebound from a prior collapse. This is not just theory. Numerical simulations and analytical models in LQC show that the universe can evolve through a bounce without encountering a singularity. The equations remain well defined. Space and time continue. The laws of physics survive. Could we find evidence that a universe existed before our own? One possible source is the cosmic microwave background, the leftover radiation from the early universe. Some researchers propose that anomalies or patterns in the CMB, such as concentric circles or specific polarization modes, could be echoes from a previous cosmic cycle. Gravitational waves are another avenue. A violent bounce could send ripples through space-time that might leave detectable imprints. Future detectors, more sensitive than anything we have today, may help search for these primordial signals. Another speculative idea is that certain features of the early universe, such as the formation of massive black holes shortly after the Big Bang, might be better explained if those structures predate our current cycle. While we lack definitive proof today, advancing technology continues to sharpen our cosmic vision. While the Big Bounce is elegant, it faces major scientific hurdles. Entropy is one of the most profound. According to the second law of thermodynamics, entropy, or disorder, always increases. If each bounce carries forward the entropy of the last, the universe would become increasingly disordered over time. Our low-entropy early universe is hard to reconcile with a long chain of previous cycles. Some models attempt to solve this. One idea suggests that entropy gets diluted during the bounce or that it escapes into hidden dimensions. Others invoke ekpyrotic contraction, a very slow, smooth collapse phase that resets the universe's initial conditions. Cosmic inflation, the standard explanation for the universe's rapid early expansion, also competes with bounce models. While bounces can provide alternatives to inflation's smoothing effects, many bounce theories now incorporate short bursts of inflation to match observations. Finally, there is the issue of dark energy. Our universe is currently accelerating, driven by this mysterious force. If this acceleration continues forever, the universe may never contract, preventing a future bounce. For a bounce to happen again, dark energy would need to fade or change behavior. These are not fatal flaws, but they are significant questions that scientists are actively working to answer. Each challenge is an opportunity to learn more about the fabric of reality itself. The idea of a cycling universe is not new. Ancient Indian cosmology described the universe as undergoing infinite cycles of creation, destruction, and rebirth. The Greek Stoics believed the cosmos was periodically destroyed in fire and reborn. Even modern thinkers like Nietzsche pondered eternal recurrence, the idea that everything might happen again and again. The Big Bounce brings this mythic idea into scientific conversation. If the universe has no beginning or end but only phases, then time itself is redefined, not a line but a loop. This raises profound questions. Could traces of previous universes persist? Could patterns, constants, or even information pass from one cycle to the next? Might the laws of physics themselves evolve across bounces? Philosophically, the Big Bounce offers a vision of resilience. That even in the face of cosmic destruction, the universe regenerates. That endings are temporary. That every collapse is a prelude to rebirth. Perhaps this is nature's way of saying nothing is truly lost. The Big Bounce is more than a theory, it's a new way to think about the cosmos, a shift from a beginning to a continuum. It suggests that we are not the first, that our universe carries the legacy of an earlier one and perhaps will give rise to the next. We don't yet have all the answers. The evidence remains elusive. The math, while promising, is incomplete. But the idea endures because it is powerful. It challenges us to ask bigger questions. What came before time? Can the universe heal itself? Could existence be eternal? As we study the cosmos, the Big Bounce remains one of the most fascinating possibilities, a theory that transforms the end into a beginning. And so we look to the stars, not only to glimpse our future, but to search for our past. The universe collapsed. The universe bounced. The universe began again. If you want to keep uncovering the secrets of existence, make sure to subscribe and follow along.